Okay, the next speaker is Paul Heslop from Queen Mary, and the title of his talk is MHV amplitudes and anything for superangles and coastal loops.
Okay, thank you. That's the second. Okay. Thank you very much. So, yeah, this is based on work with Andreas Brandhuber, Gabriele Travaglini, and Bill Spence in forthcoming work. Okay, so it's going to be closely related to James's talk with some slightly different emphases, I guess. So we're going to look at these a priori unrelated objects in n equals 4 Young-Mills. Firstly, the planar MHV gluon scattering amplitude. Secondly, Wilson loop over a curve determined by the external momenta. And Alde and Maldacena have shown that these are equal to each other at strong coupling. And we're going to show in this talk that they're equal at one loop. And then I'll say a few things about higher loops. And also see the work of Drummond, Hen, Kwiatkowski, and Sokochev for higher loops. Okay, so summarizing briefly, I don't need to say much because the next talk is by Fernando Alde, but Alde and Maldacena showed how to calculate amplitudes using ADS-CFT, and they found that at strong coupling it's equivalent to the calculation of a Wilson loop. And the Wilson loop is defined by a contour whose edges are the momenta P1, P2, P3, P4, P5 of the amplitude. So obviously we have momentum conservation. The sum of the momenta is 0, which tells you that you get a closed loop. So what happens at weak coupling? Okay, so first of all, what are we discussing here? Well, James also summarized this a bit, but if you take an amplitude, has gauge index dependence, which is factored off in the planar theory, and you discuss what's called this partial amplitude, where there's no color dependence. And then in n equals 4 Young-Mills, the higher loop amplitudes are in fact proportional to the tree theory amplitudes. And it's this Mn that we'll be discussing when we talk about the amplitude. For MHV, yes, thank you. So I haven't mentioned MHV there. This is all for MHV diagrams. Also, James mentioned that these things need to be regularized, which we do using dimensional regularization. We do things in 4 minus 2 epsilon dimensions. Okay, good. So at one loop, the MHV diagrams are given as a sum over two mass-easy box functions. So this was shown in 1994. This is up to order epsilon. We'll discuss this in a moment. So two mass-easy box function is a box function where the two incoming particles here are massless. These will be two of the momenta of the amplitude. And the opposite corners, these momenta are massive. And in fact, these will be sums over the momenta between little p and little q. So they're massive simply because they're the sums of massless momentum. And this two mass-easy box function can be calculated to all orders. It's not easy, but it's been done. And this is the result. So we have these kinematic invariants, big P squared, big Q squared, S and T related like this. This f function here is a hypergeometric function depending on epsilon. And A is related to kinematic invariance. So this is an all-order expression, all orders in epsilon. And the top line give you the infrared divergences. This is infrared divergent. The second two lines are in fact finite. So one could take epsilon to 0. So that's what it says there. The second and third lines are finite. Now the divergent, so the top line, in fact when you sum up, I mentioned that the amplitude is a sum over the two mass-easy box functions, then the multi-particle divergences cancel. And then the infrared divergence simply becomes a sum over these single particle poles. And we're going to try and reproduce not just this expression, but the whole expression using Wilson loops. So, how do you calculate a Wilson loop? Well, you basically, at one loop, you take a propagator between any 2 points on the curve, and you integrate the 2 endpoints around the curve. So if you've got a polygon, then there are 2 diagrams which contribute, this one and this one. This means that the 2 sides are adjacent. Here, the 2 sides are non-adjacent. And you could consider one ending on the same side, but that vanishes for like sides, for like edges here. So diagram 1 is the so-called cusp diagram. And it straightforwardly gives you the poles that we're looking for, the infrared divergences. We use Feynman gauge, but the thing should be gauge independent. The out for the sum, yes. So the second diagram, the Wilson loop, gives a simple double integral. So it's a nice expression. You've got 2 integration variables from 0 to 1, and they occur bilinearly here. This just comes from the propagator. Okay, I mentioned these are the same kinematic variables as before. And the outcome is precisely the second and third lines of the MHV diagram. In other words, the finite part of the MHV diagram to all orders in epsilon. So as before, it's finite, and so you can take epsilon to 0, and then you can also look at the 4-point case, which was first found by Drummond, Korczynski, and Sokochev. That was the log squared S over T that we heard about earlier. Okay, so let's just summarize that. So the one loop Wilson loop, in fact, calculates the one loop MHV scattering amplitude to all orders in epsilon at 4 points. So at greater than 4 points, we can no longer say this for the following reason. So at n greater than 4 points, the Wilson loop calculates the one loop MHV scattering amplitude just to finite order for the following reason. The 5-point amplitude, just take an example, the 5-point amplitude is given by a sum over 2 mass easy box functions, that was the bit that we've calculated, plus a pentagon term which appears at order epsilon, multiplied by this tensor structure here, which is parity odd. Okay, so this bit is not calculated by the Wilson loop. And this is also doesn't appear to be conformal, or not in the standard sense anyway. So the Wilson loop misses these pentagon diagrams. At 4 points there are no pentagons, and then we can make the strong statement that the Wilson loop gives the full answer to all orders in epsilon. I also already mentioned that there's this parity odd term, so that one can make the statement that the Wilson loop at 5 points does give the parity even part of the amplitude to all orders in epsilon. However, even that statement cannot be made at 6 points.
Will it be right to say that the sum of all 2 mass easy boxes is represented by one loop contribution to Wilson line to all orders in epsilon?
Yes, that would be correct, yeah. Okay, so let's now briefly talk about higher loops. So James mentioned the BDS conjecture, so I don't have to say much about that, but it's given by an exponential of terms involving the one loop amplitude plus order epsilon. And then there's this nice non-abelian exponentiation theorem for Wilson loops, which gives this in terms of an exponential as well. So if these two guys are in any sense equal, then we at least want that this little w that appears here is equal to the one loop to this expression. But this is a weaker statement than actually saying that the Wilson loop and amplitudes are equal, as we'll see. So here the advantage of the non-abelian exponentiation theorem is that this little w is a subset of the full number of diagrams that you have to calculate. So at 4 loops, at 4 points, the 2-loop calculation is done by Drummond et al., and you look at these diagrams. And it agrees with the BDS conjecture. So it's been calculated up to order epsilon to the 0, this term. And also the 5-point recently, earlier this week, as we've heard, was also calculated. So we're in the process of calculating the 6-point Wilson loop at 2 loops. And as we've seen, this isn't just a game of going to higher end loops, because the 6-point case is going to be a crucial test from the point of view of conformal symmetry. But in the meantime, given that we don't have the results at higher loops yet, let's try and make some conjectures and some observations about what we can and cannot expect for higher loops. So at 4 points, one can make a conjecture which is consistent with the available data, a very strong conjecture. One could make that the Wilson loop is completely equivalent to the 4-loop amplitude to all orders in epsilon. Okay, so far we only have the one loop result, and we see that this equality holds at 1 loops. 2 loops, we only know it to order epsilon to the 0. So you might, I mean, we don't know the answer to all orders in epsilon, so that remains to be shown at 2 loops. Nevertheless, a weaker statement might only hold in that they're only equal up to order epsilon. This is for 4 points. Now, I want to hasten to add that at 5 points, even at 5 points, at 2 loops, even this weaker statement is not quite true. And that's precisely because of these parity odd terms. So I showed you the parity odd term at 1 loop. There's also a parity odd term at 2 loops, which is eventually calculated in 2006 by these people. And the problem at 2 loops is that this parity odd term comes with a 1 over epsilon. So therefore I cannot make this statement. And the parity odd term can never appear in a Wilson loop calculation. That you can see very easily from the calculations, from the sorts of calculations you do. Another interesting point is that this seems to violate conformality. And another interesting point is that it vanishes in the collinear limit. So what conjectures can we make at endpoints? Well, one could make a weaker conjecture that the log of the amplitude is equal to the log of the Wilson loop plus order epsilon terms. So this is a slightly weaker conjecture for the following reason. Let's see what consequence it has at 2 loops. At 2 loops, if you expand out this log, you get this combination, m2 minus a half m1 squared. And the BDS conjecture says that that's equal to this right-hand side. So this weaker conjecture would say that the Wilson loop has the same right-hand side, where one could also replace this with the Wilson loop, because the Wilson loops and the amplitudes are equal up to order epsilon. Okay, now this seems to contradict the fact that the 5-point terms have these parity odd pieces in them, which the Wilson loop doesn't calculate. However, there's a parity odd piece here at order 1 over epsilon, as I mentioned, but there's also a parity odd piece here at order epsilon, this pentagon, and because m1 has order 1 over epsilon squared, then there's a parity odd piece of 1 over epsilon and a parity odd piece at order 1 over epsilon, and these precisely cancel. So that's quite a strong statement about the BDS conjecture found in 2006. And that's a strong statement because the parity odd pieces are not found by the collinear limits. So, okay, I didn't talk about the collinear limits, but the collinear limits put a strong constraint on the BDS conjecture, strong consistency conditions. Okay, so that was the sort of weakest conjecture one could make at endpoints. So now a slightly stronger conjecture, which it would be nice if it were true, is that the Wilson loop calculates certain integral functions that contribute to the amplitude, perhaps even to all orders in epsilon. So that's what we saw, for example, at one loop, that the Wilson loop calculates the MHV, the two mass easy box functions. And then one, consistent with the data so far, is that the integral functions that are missed by the Wilson loop are precisely the ones that vanish in the collinear limit. Okay, so one could speculate that that continues to hold. And then at 5 points, there's also this idea about the parity even, parity odd part. So one could hope that the Wilson loop calculates the parity even part to order epsilon to the 0. This is still possibly true because the even parts separately exponentiate, which is shown at 2 loops in this paper. But in fact, it's possible that it could hold at higher loops because these parity odd squared terms, according to BDS, will occur at order epsilon. Oh, this you can see quite easily. Okay, so the reason this is only true at 5 points, though, is because at 6 points there is a hexagon graph at order epsilon. So at 6 points you've got the sum over 2 mass easy box functions plus this hexagon graph multiplied by this kinematic invariant multiplied by epsilon, which also interestingly happens to be conformal. I don't quite know what that means. And this vanishes in the collinear limit, so that's why I say that this statement is consistent with the known data. Okay, so the final conclusion is pretty much the same as James's final conclusion, which is we need to do more calculations, in particular 2-loop amplitudes at n greater than or equal to 6 points, and we also need, it would be also nice to get expressions for all orders in epsilon for 2-loop 4 and 5 point functions. Okay, thank you.
Any questions? Well, if not, I suggest we all go out and calculate and come back again.